In this lecture, we're going to see a way we can transform from a shared pointer to a unique pointer. And sometimes you have a use case like this. You have a unique pointer, for example, unique PTR int1 or unique PTR dog1, which are pointers both to dog and int. And you want to have multiple pointers, but because we have a unique pointer, we can't really make a copy. So what you can do is make a transformation from a unique pointer to a shared pointer using the syntax that we have here. The way you do this, you set up a variable of a shared pointer type. For example, the first one is a shared pointer to int. The second one is a shared pointer to dog. And then we move memory ownership from the unique pointer to the shared pointer using the syntax here. And the trick is to do an std move. This is going to move ownership from the unique pointer to the shared pointer. And the shared pointer is going to be managing our memory now. The unique pointer is going to be reset to null pointer, and it's no longer going to be pointing to the memory where it was pointing before. The same is true for the shared pointer to dog. Ownership is going to move to the shared pointer, and for all of these shared pointers, the reference count is going to become 1 because we just have one shared pointer pointing to our data in memory. This is what we can do. But please note that you can't directly assign data from a unique pointer to a shared pointer. If you do this, this is going to give you a compiler error because that's going to violate the uniqueness of your unique pointer. So the compiler is not going to allow you to do something like this. From this point on, the shared pointers are going to be managing our memory. If we print the use count, we're going to get 1 and 1 because we have one of each pointer pointing to the data in memory. And we can use these shared pointers however we want in our program. For example, here we are casting them to bool so that they are usable in if statements, for example. You can do all kinds of crazy things. But one thing you can't directly do is transform from a shared pointer to a unique pointer. This is not going to work because at any given moment, we might have multiple unique pointers pointing to the same data in memory. So if you take one of those shared pointers and make it into a unique pointer, it wouldn't really make sense of what you make of the other shared pointers that were pointing to that memory location. And you should really have one unique pointer pointing to one piece of data in memory. You can't have multiple pointers pointing to that piece of memory. So hopefully you can see that what we are doing here is really conflicting. We can't do this through braced initialization. We can't do this through assignment. And we can't do this through an std move. This is not going to make sense. So if you do this, you're going to get a compiler error. You should know this. But one thing you can do is return a unique pointer from a function. For example, here we have a function which is going to return a unique pointer. We can assign this unique pointer to a unique pointer. This is what we are doing here. We have an std unique pointer to dog, and we are assigning the return value of getUnique to this unique pointer here. So this is going to move ownership from the pointer in the getUnique pointer function, and ownership is going to move to this external unique pointer, and it is going to be the only pointer pointing to this memory location. Another thing we can do is assign the return value, which is a unique pointer, and assign that to a shared pointer. This is going to compile just fine, and what this is going to do is going to do an implicit move from the internal unique pointer to the function, and ownership is going to move to the external shared pointer here, and we're going to have a reference count of 1. Okay, so this is what we're going to have here, and this is really similar to directly moving ownership from a unique pointer to a shared pointer, just like we do in this comment here. This is going to work, and you can use this pointer however you want in your own programs. And as a word of caution, having a function's return pointers is going to make your code flexible because you can take a unique pointer and turn that into a shared pointer, but you can't do the reverse. You can take a shared pointer and make it a unique pointer. So if you happen to want to return a smart pointer from your functions, returning unique pointers is going to give you much more flexibility. So you should keep this in mind. Okay, so now that you know this, we're going to head over to Visual Studio Code and play with this a little more. So here we are in our working folder. The current project is shared pointers from unique pointers. We are going to grab our template files. Let's do that. And we're going to put them in place. And another thing we're going to do right here is to steal the dog class from previous lectures. So we're going to do that. Let's copy it. And we're going to put that in our current directly so that we don't have to create this class from scratch. And then we're going to open this project in Visual Studio Code by dragging and dropping here. We can close the left sidebar, but before we do that, let's open our files. We can also open the main CPP file, no problem. And we're going to clean up. Let's do this, and we're going to include memory to have access to shared pointers. And we're going to include our dog class. We are going to go down and put in our code. The code is going to set up a pair of unique pointers. Pointer int1, which is a unique pointer to int, and we have a second pointer, which is a unique pointer to dog. We're going to create a dog object, and these objects are going to be heap objects. You should really know this. Let's say that as clearly as we can. Okay, so they are heap objects, and because we have unique pointers, we can't really make copies. And suppose we want to make a copy of these objects that we have on the heap. One thing we can do is turn these unique pointers into shared pointers. And one way to do this is to do an std move and move ownership from these unique pointers to shared pointers that we have set up in our code here. Now shared ptr1 is going to be pointing to this int object, and shared ptr dog1 is going to be pointing to this dog object here. And these pointers we had before, the unique pointers, are going to become useless because they are going to be just pointing to null pointers. So that's what you should know here. Another thing you should know is that you can't really directly transform from a unique pointer to a shared pointer. If you do an assignment like this, you're going to get a compiler error. So let's comment this out because we're going to have a chance to look at this in a little more detail in a minute. But for now, we just want to see that these shared pointers are now copyable because we can create more copies of these shared pointers. Let's print the use count here. We're going to see that we're going to get a 1 because for now we just have one of each pointer pointing to the data in memory. For the int pointer, the use count is going to be 1. For the dog pointer, the use count is going to be 1. And we can really do all kinds of crazy things with this. For example, we can cast this to bool. If that is making sense for the problem we are solving with C++, we can do all kinds of crazy things. For now, we're going to bring up a terminal window or a PowerShell window, and we are going to build with GCC. So let's do that. This is going to build successfully. As you see here, we can clear and run Rooster. This is going to give us a use count of 1 for all these guys because we just have one shared pointer pointing to our data in memory. Another thing we can do here is try and see what we have in these unique pointers now. Let's do that. We're going to go down and we're going to say stdc out unique ptr int1, and we're going to print that out. It is int1 here. And we're going to do the same for the dog pointer. Okay, we can do this, and let's say int1 exactly as we have in our code. This is going to make it easier to follow. We're going to build with GCC. Okay, the build is good. We can clear and run Rooster. Now we see that our pointers are really pointing to null pointer. That's what we see here. And this is really cool. We have successfully transformed from a unique pointer to a shared pointer. And now that we have a shared pointer, we can create copies of these pointers and have multiple pointers pointing to the same data in memory. And this is really cool. Okay, so let's go down and create our copies here. We're going to be making copies, and we're going to set up a shared pointer 3, which is going to copy shared pointer 1. And we're going to do the same thing for dog. And if we print the use count, we should see the use count go up for pointer 1 and pointer 3. Let's do this. We're going to run and build with GCC. And we're going to clear. The build is good. Let's clear properly and run Rooster. Now we see that we have a use count of 2 for all these pointers here because we really have 2 shared pointers pointing to the same data in memory for int and dog pointers here, and this is really cool. One thing you can't do is try to directly transform from a shared pointer to a unique pointer. If you do this, you're going to get a compiler error. And the reason is what we said in the slides earlier. For any shared pointer you have in your code, we can have really many other pointers pointing to the same data in memory. And if you take one of those pointers and turn that into a unique pointer, what's going to be of the other shared pointers? That's one point. But another point is that for a unique pointer to be a valid unique pointer, there should only be one unique pointer pointing to the same memory address. But we happen to have multiple shared pointers pointing to the same data in memory. So this should really be enough information to tell you that this is something dangerous to do, and the compiler is going to prevent you from doing this. If we try and build this program, we're going to get a bunch of weird compiler errors. Let's see. This is really bad. We have errors we can't really make sense of. This is typical C++. Don't be afraid of this. Just to make sure you understand why this is not working, because we really are trying to violate the uniqueness of a unique pointer by trying to assign it a shared pointer which might have multiple pointers pointing to the same data in memory. Okay, so if you try to look to the error here, default delete, we can't really make sense of this as of now, but know that this is something you can't do, and if you do it, you're going to get these weird compiler errors, so be warned. Another thing I said I would talk about later in this lecture is that you can't directly transform from a unique pointer to a shared pointer. If you try to do this, you're also going to get a compiler error because this is a bad assignment. We can't assign a unique pointer to a shared pointer. That's not going to work. And the reason is the C++ compiler is trying to protect you from doing what you are doing here. If you want to do an assignment like this, you have to do an explicit std move and say that you want to move ownership from this unique pointer. This is not clear enough what we have on line 16. You are doing this assignment, but the compiler doesn't really know that you want to give up ownership from unique pointer 1. Again, if we try and run this, we're going to get a weird compiler error. Hopefully it is going to make sense, but let's see. We're going to see conversion from unique pointer to dog to shared pointer to dog requested, and this is not allowed. We're going to get a compiler error. Let's comment this out now that you know this. And we're going to try and build and make sure that we have a clean build. Okay, the build is good. Okay, now that we have this done, another thing I want you to see is how you can return a unique pointer from a function. And this is nothing sophisticated. We can just return our unique pointer to dog by value. And inside our function, we're going to set up a unique pointer which is internal to this function, and then we're going to return it. This is going to work because C++ compilers are going to do some magic to return a reference to the unique pointer we have internally in this function here, and this is going to work. So one thing you can do is return this unique pointer and assign it to a unique pointer. That's going to move ownership from the inside to the pointer on the outside, and we're going to look at this in a minute. But we can also return this unique pointer and assign that to a shared pointer. This is going to do an implicit move from the internal unique pointer to the outside shared pointer, and we're going to look at this right now. Okay, so let's come down here to line 64, and we're going to put in our code. We're going to put in a call to our getUniquePointer function, and what we return from that function is going to be assigned to a unique pointer. This is going to move ownership from the internal unique pointer to the outside unique pointer we have here, and we can use this unique pointer to do all kinds of crazy things. For example, we can print out whatever name we have for this dog, and we're going to see it printed out here. So let's go back and see the name we have for our internal dog. We have Phil, that's the name for the dog, so that's cool. We're going to build. And we're going to have a clean build. As you see here, we're going to clear and run Brewster. Let's go down and see what we have. We're going to construct the object inside the function. We're going to return that. And then we're going to destroy our fill dog because it's no longer used. We're just going to hit the end of the main function. But before we hit the end of the main function, we're just going to print the dog name, which is what we have here. I'm going to say unique pointer dog name, and we're going to print the name here, and that's what we have here. This is working exactly as we would expect. We're going to go down and show you that we can also do the same thing, basically returning a unique pointer, but assigning that to a shared pointer. Again, that's going to move ownership to the outside shared pointer. Okay, so let's go down here to line 74 and put in our code. We're going to return a unique pointer to a shared pointer. And this is exactly what we are doing here. We get a unique pointer. We assign that to a shared pointer. This is going to implicitly move ownership from the inside unique pointer to the outside shared pointer here. And the shared pointer is going to have a reference count of 1 because we just have one shared pointer pointing to our data in memory. We can get the name of the dog. We can print the use count. We can do all kinds of crazy things. Let's just build and see that this is working. Okay, the build is good. We can clear and run Rooster. If we go down, we're going to see that we are returning a unique pointer from a function and assigning that to a shared pointer. We're going to have shared pointer, dog for name, that's going to be Phil. The reference count is going to be 1. And then we're going to be destroying all the dog objects that we have here. And this is really cool. We have 3 dog objects that need to be destroyed. We have Phil and Phil, one coming from the shared pointer here, the other coming from the shared pointer here. So that's going to give us 2 dogs. If we go on top, we're going to find another dog, which is pointed to by all these pointers here. And that's going to be destroyed as well. And the name happens to be Halls, and that's what we see destroyed here. And this is really cool. This is really all I had to share in this lecture. But another point worth mentioning again is that if you have to return a smart pointer from a function, it is really much more flexible to return a unique pointer. Because you can turn this unique pointer into a shared pointer, but you can't do the reverse. You can't turn a shared pointer into a unique pointer. You should really know this. So this is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this one. In the next one, we're going to explore how shared pointers work with arrays. Go ahead and finish up here and meet me there.